everyone, let's hear about the key concepts from the IB chemistry theme. Reactivity 2, summarized in the question, how much? How fast? How far? These questions relate to quantifying chemical change, understanding reaction rate, and predicting equilibrium position, essential for grasping how reactions behave in the real world. This section is all about calculations in chemical reactions. We use stoichiometry to determine the amounts of reactants and products. You'll often use formulas involving moles, mass, volume, and concentration, which are shown in the triangle diagrams in the poster. Two important concepts are percentage yield equals actual yield divided by theoretical yield times 100. This tells us how efficient a reaction was. Atom economy equals the molar mass of the desired product divided by the molar mass of all products, times 100. This relates to sustainability. Higher atom economy means less waste. These are vital when discussing industrial processes or green chemistry. Here, we focus on the rate of reaction, or how quickly reactants are converted to products. The factors that affect rate include concentration, temperature, surface area, pressure for gases, and presence of a catalyst, which lowers the activation energy. The poster highlights the Arrhenius equation, which links temperature and activation energy to the rate constant, K. You'll notice that as temperature increases, the rate increases. This is shown in the graph included. The key idea is more frequent and effective collisions equals faster reactions. This section deals with chemical equilibrium, where the rate of the forward and reverse reactions are equal. The position of equilibrium can shift depending on concentration of reactants or products, temperature, Le Chatelier's principle, and pressure, especially in gases. For example, if you increase the concentration of a reactant, the system shifts to produce more product. Increasing temperature favors the endothermic direction. The equilibrium constant, K, tells us the extent of the reaction. K greater than 1 means products are favored. K less than 1 means reactants are favored. After understanding these concepts and its uses and importance in various chemical industry, we should ask bigger questions. Hence, we would like to relate some TOK questions to the topic. After understanding these concepts and its uses and importance in various chemical industry, we should ask bigger questions. Hence, we would like to relate some TOK questions to the topic. Are yield or rate limits absolute, or can technology overcome them? What are the ethical implications of producing certain chemicals or using specific byproducts? For instance, in pharmaceuticals or fertilizer production, should we prioritize maximum yield, safety, or sustainability? These questions should help us in the future to explore our knowledge deeper, allowing us to discover various new alternatives and continue the pursuit of knowledge. Next, moving on to the global issue of how this theme, how much, how fast, how far, connect to a pressing global issue, China's heavy reliance on coal combustion. Coal is still the dominant energy source in China, and that brings up huge questions about energy efficiency, pollution, and climate impact, all of which are deeply connected to chemistry. In the how much occurs section, we deal with stoichiometry, enthalpy changes, and atom economy. When coal, mostly made of carbon, burns, it releases a known amount of energy, as shown in the equation. In China, billions of tons of coal are burned every year. That means an enormous amount of CO2 emissions. So this raises a key question. How much energy do we get versus how much environmental damage do we cause? Improving percentage yield and atom economy could reduce waste and emissions on a global scale. Even small changes have big impacts when scaled to China's consumption. Next, How fast deals with reaction rates and the Arrhenius equation. In China's coal plants, combustion reactions are optimized for speed and heat, but higher temperature saw faster reaction, but also more NOx pollutants from nitrogen in the air. Catalysts can reduce the activation energy, making combustion more efficient with less pollution. These bring us to the fatal aftermath of the reliance on coal combustions. Burning coal releases CO2, SO2, NOx, and PM2.5 particles, all linked to global warming, acid rain, respiratory illness. China's massive coal use has global effects, not just local ones. And while the country is investing in green energy, coal is still a key part of the grid. So the global issue becomes, how can we meet rising energy demands without sacrificing environmental health? And that's exactly where these chemistry concepts become useful. To summarize, the three chemistry themes, how much, how fast, how far, help us break down the real-world chemistry of coal use in China. They show us how to think critically about energy, pollution, and sustainability, which are not just chemical concepts, but global concerns.